This video is going to be our last video on trees. So, as we mentioned at the end of the video on binary search trees, the efficiency of the search on a binary search tree is dependent on whether or not the tree is balanced. So, if the tree is balanced, then we can expect to get the most efficient possible search in the log n time range, big O. Okay. So, in the worst case scenario, we have a tree such as the one I have here. If we add numbers sequentially, one, then two, then three, then four, and so forth, the search for this one is going to be the same as it would be for a sequential search, right? If we're searching for a six, we'd have to start at one and then go to two and then three and then four and then five and then finally determine that there is no six. Okay. So we totally diminish the advantage of having a binary search tree if our trees become unbalanced. So there's a fair, sorry, allergies, not good this morning. So there's a fair bit of research that has been done on self-balancing trees or a tree that will maintain itself in some sense of balance. And that sense of balance is going to vary based on the algorithm. So the first kind of tree we're going to talk about here is going to be an AVL tree. So it's named for the people who came up with this Adelson, Velsky, and Landis. So it starts with the idea of a balance factor. So every node in an AVL tree has a balance factor, which is calculated by taking the height of the left subtree minus the height of the right subtree. So by definition, every node in an AVL tree should have a balance factor of zero, which means it has the same number of left and right, or it can vary by one, which gives us a one and a negative one. Okay, so that we're going to allow that much imbalance. And that makes sense because you have to have some imbalance. If we add a two to a new tree, and AVL trees are binary search trees, so we have a two as the root. Uh, Any leaf node is going to have a balance factor of zero because it has a zero for a left and a zero for the right subtree. If we add five to that, it would go to the right of the two. We're now imbalanced in that it would be the left is zero, the right is one. So zero minus one is negative one. If we didn't allow that, we just couldn't have trees, or we would have to always add a full level of trees as we went along. So that's why that's allowed. Um, so once we can calculate this balance factor, and in code, it basically we're gonna in our struct for a node, the binary search tree node, we're gonna add to that a balance factor. So every single node will be able to calculate its own balance factor. Okay. If things get out of whack, okay, things get out of whack, an AVL tree is balanced, at least in this way, mostly balanced. If we insert something or delete something, we have to make sure that we haven't upset the balance. Okay. So to fix the imbalances, depending on what the values are, we have four different transformations because there are four different scenarios we're going to have. And I'm going to name them here, and then we're going to go through some examples of those. Okay. The first would be a right-right rotation, then a left-left rotation. And it's odd that they call them right-right and left-left. There's just they're only one transformation. But then there are the complex ones, the left-right and the right-left. Okay. And that's for when you're at a node, you've inserted a node, they're a binary search tree, so you have no option where you put it. You put it where you put it, and then you check. Of course, the new node will have a balance factor of zero because it's a leaf node. But as you move up to its parent and then its parent, we're going to call the insert recursively so we can unwind or unfold the recursions to go back to a higher level. Okay, as we go. Okay. So in this first example, let's say we have an empty tree. We insert a one. So at this point, the balance factor for the 1 is 0 because it's a leaf node. We're then going to insert a 2. So the balance factor at node 2 would be 0, but the one here is going to be 0 minus 1. So that's a -1. We're still good. But now when we do this 3, okay, it's going to be 0 for the left subtree of 1. So again, 3 is okay. 2 is okay. 2 has a balance factor of -1, but 1 has a balance factor of -2. And that's a problem. Okay. So to do this, we're going to do a right notation. And I'm not going to ask you to code this because I think it goes beyond the scope of the class and just there are time constraints. But I am going to ask you to be able to work these out on paper or on text or whatever we're doing. So in this case, visually, what we're going to do, okay, we're going to balance this by grabbing the 2, lifting it up, making it the new root. Okay. So when we've done that, node 2 is now the root. Node 1 follows over there. Node 3 follows over there. Okay. And if we look, 1 and 3, of course, are leaf nodes and have a balance factor of 0. 2 also has a balance factor of 0, the 1 minus 1. Okay. So that's the right notation. The other simple notation is a left notation. It's kind of the opposite. If we were to insert a 3, it's a leaf node, life's good. A 2, then the 2 would go to the left of 3, and this would have a node balance factor of 1. This is 0, we're good. And then a 1. Now, node 1 has a balance factor of 0, node 2 has a balance factor of 1, but node 3 has a balance factor of 2. Okay. So we're going to do kind of the opposite here, but this is the left notation. We're going to the left, grabbing the 2, pulling it up as root. Okay. Down here, and now all the nodes have a balance factor of 0. Okay. So those are the two most straightforward cases. It just require that one transition. And when you're thinking about how you would code this, again, we're not going to code it, but the thing you're doing here, you're going to be using pointers to nodes, of course. You've got your left and your right subtrees, so those pointers, and you can use a temporary pointer as a way to move things around. Okay. So that's the basic idea of those. So let's look at example 3, where we're going to insert a 3, life's good, a 1, life's still good. Okay, we have a factor here of 1 would 3, sorry, when we what has that would be a 1 minus 0 or 1. But when we insert this 2, it's going to go to the right of the 1. Okay, so the node factor or the balance factor at node 2 is 0. At node 1, it would be a -1. But at node 3, it's going to be 2 minus 0 or 2. Okay. Um, so that's an issue. So the first thing we're going to have to do, okay, we're going to have to do a left rotation to fix these two. Okay. When we do that, we're going to move 2 up, which will get us into this orientation with the 3, then the 2, then the 1. And then we're going to do the right rotation. We've already fixed that one above, which gives us the 2, the 1, the 3. Okay. So that's a solved problem once we get here. In the same way, if we insert a 1, then a 3, then a 2, we're going to end up with this kind of situation. Okay. And again, our two-step solution starts with doing a right rotation to fix these two, which gets us to the 1, the 2, the 3, which we've already solved above with a left rotation to pull the 2 back up. Okay. So again, one thing that's different when we're coding this is that we're going to add this balance factor to the struct for our we're going to call it the AVL node instead of a tree node. Okay. And we still have our R link and L link like before. Okay. So again, the insertion and deletion, both for that matter, are done recursively. So once we've added or deleted things, we start with the node we're on, we check its balance factor, we then go up the tree, checking the balance factor as we go. Okay. So again, we're not going to do the code for these. I'm most likely going to move some code over on the server so you guys can play with this as part of the homework, but you won't have to create it yourself. Okay. But I do want you to be able to work through these on paper. Okay. So here's what an example of that would look like. Okay. So I've got here at the bottom. Insert the following sequences of numbers into an empty AVL tree: 40, 20, 10, 30, 50, 60, and show the tree after each insertion and what you've done. So when we insert 40, we got a 40. The balance factor of 40 is 0. No problem. Okay. We insert a 20. The balance factor at 20 is 0. We go up the tree, and the balance factor at node 40 is 1. Life's still good. Okay. We insert a 10. The 10 gets inserted here. Again, recursively. We start here, then we recursively insert on the left child, and then do that again. So now we're here. We're going to check the balance factor for this node is 0. The balance factor for this node, as we close out this recursive step, we go back to this one that called it and see that the balance factor here is a 1. Close this one out, we're back to here, and the balance factor is a 2. Okay, so we need to do our right rotation, okay, and pull this one up. Okay, that's actually a left rotation. I get those confused because it's moving to the right, but we go to the left to grab the 20 to pull it up. We now have our 20, our 10, and our 40. Okay, we now go to insert a 30. So we're at 20, 30 is bigger. We go to the right to 40. Recursively, 40 is bigger, so we recursively go here, and we can place it here. The 30 goes there. Okay. So the balance factor at 30 is 0. It's a new node. At 40, it's going to be a 1. 1 minus 0, okay, which is good. And at 20, it's going to be left child height is 1 minus 2. Okay, so 1 minus 2 is -1. We're still good. Okay. Next, we're going to insert the 50. So 50 will end up going over here. So we're at 20. 50 is bigger than that. We go here. We go to 40. 40 is bigger than that. We go to there. The node factors don't change. Again, we check 50. It's always going to be 0 because it's a new node. 40 is going to be at a 0 now. Okay. And 20 is still going to be at a -1, which is fine. Okay. Then we insert a 60. The 60 goes down here at the bottom. Okay. So the balance factor of 60 is, of course, 0. The balance factor at 50 is going to be a -1. Okay. Which is okay. The balance factor of 40 is 1 minus 2 or -1. It's okay. But the balance factor at 20 is going to be 1 minus 3 or -2. Okay. So at 20, we're going to basically, the idea here is going to be to do a right rotation, grab the 40, move it up. Okay. So as the 40 moves up, the 30 has to go with it. Okay. And then you have the 20 and the 10. And depending on how you implement it, I think in some ways you can implement this. The 30 would end up going to the right of the 20. So you've got some competition here. You have to choose which has precedence. What was already at the 10 here, the 10 that's already part of the 20, or the 40 the 30 that's coming in. Okay. But if you do it this way, then you check the nodes and find out that's out of balance, and you end up with this tree. And this is the correct balanced tree. Okay. So when we delete a node, you again have to make sure that the tree's still balanced, and you delete in a recursive fashion as well. So from this tree, if we delete the 60, okay, we would have to calculate that the 50 is, of course, now a 0, and the 40 is 2 minus 1, which is a 1, so we're still okay. But if we would then delete a 50, now we're in this situation, okay? So this would be a 2 minus 0, or 2. So we have to do a left rotation to grab the 20, pull it up, and that will take care of our things here. Okay. So that's the basic idea of the AVL trees. Okay. And they're pretty common. The disadvantage to an AVL tree is that as the tree gets bigger and bigger and bigger, the balancing can take a while. It's always balanced. So when you add a new node in a complex enough tree, it could trigger lots of changes and lots of changes and lots of changes. So it could be computationally expensive. Okay. So there are some other strategies that people have come up with in order to deal with this. And I think probably the most um, used and the most useful one is a B tree. Okay. B does not stand for binary. It's not a binary tree. It's a B tree. It's a different thing altogether. Okay. So what a B tree does for us is it allows each node to hold more than one bit of information. Okay. So each node can hold whatever the order of the B tree. You can have a B tree of node five, which will hold five, up to five per node. You can have a B tree of 100,000, million, whatever you want. Okay. For the order. Okay. And what this does, this is in essence like indexing. Okay. So, like when you go to create an encyclopedia, which you've probably never seen, but back in the ancient past, before the internet, we had to look in these series of books, which was supposed to have something about nearly everything. Okay. That got way too big to hold in one book. So we would divide it into volumes. Okay. We would have a volume where we would go to the A or the B or whatever, and it would subdivide that. Okay. Um, so that's kind of the idea. Or look at a filing system where you're going to have maybe stuff by state, by city, by whatever, in order to break it up. Okay. So with a B tree, you're trying to minimize the number of levels that you have. Okay. Um, so that's kind of the idea there. Okay. Again, the advantages are that you can store a lot more information. So a binary search tree, just a normal one, or an AVL tree for that matter, of a height three is only going to be able to store seven pieces of information. But a B tree of order three, okay, or of height three. So I say order three here, but that's not right. Of order three, no, of height three. Yeah, of height three. I got it correct. Um, would be able to hold three in the root node, and then each of those three would have three in the second level, and then each of those three would have three in the third level. So three times three times three, or 27 bits of information. Okay. And the way these work is you're adding them. Okay. And you don't net you keep the root as as one as long as you can to fill out the things basically. But in this case, when we have a multiple node, so the 20 and the 40 is at the node, we now have three child links here. Okay. So at the 20, these are things that are less than 20. These are things that are greater than 20. In this case, we have this link is still less than 20, anything that's less than 20. And at the same level, we could have three things here. We could have a 10, 9, 8 could be here, would be fine. This link are for items that are between 20 and 40. We could have 30, we could have 25, we could have 38. All could be here. Okay. And then this link are going to be for items that are greater than 40. Okay. And again, in our order of three, we could have a 50, 60, 70 here. Okay. So that's the basic idea of how the B trees work, and they're really important. They're important in database development and in lots of places. Okay, but again, time constraints mean we're not going to be able to code these up here, but you'll most likely see them someplace else. Okay, and then there's a 2-3 tree. The 2-3 tree, it's a it's going to be a balanced search tree, but not necessarily, or it's not going to be a traditional binary search tree. There's no binary on this one. In that, we're going to allow some nodes to have three bits of information, sorry, 2 bits of information and 3 links. A normal node in a binary search tree has 1 bit of information and 2 links, 2 children. We're going to allow some nodes to have 2 pieces of information with 3 links, just like we did for the B tree as far as how those links get determined. Okay. What this does for us, it allows us to defer balancing. Okay. So we can hold off a little bit longer before we have to balance. So fewer balances depending on other factors. The fewer the balances you have, the better the performance is going to be. Okay. So that's kind of the idea there. And then the last one that we often talk about but don't do much with are red-black trees. And a red-black tree, it's a binary search tree, but it has an extra bit that it stores in the node that will mark each node as either red or black. And then there are ways to determine how to make it red, how to make it black, and different rules that you have, such as the root has to be black, and there are no two red nodes adjacent, and all that stuff. Um, and it always seems to me a fairly convoluted way to do things, but the idea there is um, to keep the tree balanced in some degree. And we don't see those as much at all. Okay. So that's the basic idea of that. I think what I'm going to do now is show you an example of some code that works. The book has, if you go to the book website, you should be able to get to that. You can get this AVL code, or this may not be their AVL code. I don't remember. I got this from where I've taught this before, so I'm not sure exactly where this code came from. It doesn't 100% look like I did it, but I probably tweaked it. So anyway, so in this particular example, which tells me I didn't do it entirely, they're using a class instead of a struct for the AVL node. It doesn't really matter much. They're not adding any other features to it, and a struct would work just fine here. Okay. So we basically have the info, we have this balance factor we've introduced, and we have the links to the left and the right, okay, of the subtrees, which is all pretty basic what we've seen before. Okay. And then we're going to have the following functions. Okay, so we're going to have an insert. The insert's going to be different. We have a rotate to left, a rotate to right. We have the balance from left and the balance from right, okay, which are going to be used for those left, right, and right, left transformations, okay? We then have, in addition to our normal insert, we have the insert into AVL. Okay, we're going to use that. We've seen this before when we have recursive functions where we have to have something to get us started, and the other one we're going to call recursively. That's kind of what this does. Okay. And then this is also going to have the traversals for in order and pre-order. Okay, there's not a post order, but you get the basic idea there. Okay. And then there's a function that will return the balance factor. Then there's a Boolean function, then our default constructor here. Okay. So again, we're going to have the root is going to be private. And then as we've seen before with the in order and pre-order, there are two versions. Again, we're going to be able to call that recursively. So there's the outward facing one and the inward facing one that gets called. Okay. Um, there's the search. The search looks kind of like we would have for a binary search tree. Shouldn't be anything particularly weird there. The balance factor is just an accessor function. It returns the balance factor. Okay. Um, again, that's because this is a class. If it wasn't a class, it would be public and we could just get to it. Okay. So it wouldn't be an issue. Then here's the rotation. Here's we're going to rotate to the left. It shows using the pointers here. Okay. What you would do here. So we've got this P is going to be the pointer that we're using as kind of a temporary to the root of the right subtree. Okay. So we're first checking to see if the root's equal to null. If so, there's some kind of an issue. You're trying to rotate and there's no tree to rotate. And root here will not necessarily be the root. It's the root of this recursive call. Okay. And then we're going to look to see if the right link of the tree, the subtree that we're trying to do is equal to null. There's also a problem, and then we can't rotate in that direction on this rotate to left. Okay. But if all that's okay, we're going to set P, okay, which currently points to the root of the right subtree. Okay, we're setting it here equal to that. Okay. We're going to let roots R link point to this link. So the left subtree of P becomes the right subtree of root. Okay. And then we're going to make P the new root. Okay. Oh, and then the left link of P will now point to root. The root now points to P. Okay. So this is just doing a swap. Okay. I ought to do that. Okay. Rotate to right works the same way in the other direction. Okay. And then the balance from left, we're going to go through the different cases here on what our factors look like, whether it's a -1 or a 1 or a 1. Okay. Um, and then we're going to use the switch here to go through the balance factors and how we're going to do our rotate to left and rotate to right. See, we down here, we're doing both of those things. Okay. The balance from right works in a similar way. Okay. Which gets us into our insert to AVL, but we start with the insert typically, which is down here. This keeps track of this idea, Boolean called is taller, which is helpful because if the tree doesn't change in height, we don't have to worry about it, right? If we add a node that doesn't change the height of the tree, we don't have it can't have changed any of the balance factors. So we just move on, okay? Then here's where we're creating our new node, okay? Like we would do, nothing new there. The new node will always have a balance factor of 0. And then we're going to use this insert into AVL function to send this bit of information, okay? And we're doing this basically because what we wouldn't have in our normal insert function should just take the item we want to send. That's for the user. But for us, we need to have a location, the new node we've already created, and this Boolean is taller. See what we need to do with it, okay? We then go up to this more complicated insert into AVL with that information, okay? And then it's going to go through, and of course, if root's null, life's easier. The root's equal to new node, and the is taller is now true, okay? And then we're going to go with other cases here. No duplicates are allowed. And then we have our basic division here that if the root info is greater than the new info we're adding, then the new node has to go into the left subtree. Okay. Here's the recursive part. We're now calling the insert into AVL on the root L link. Okay. And we'll keep doing that as we go along. There's another if down there. If it's not, it's going to go into the right subtree. Okay. And then after we insert, we have to figure out, did the subtree grow in height? Okay. So if it did, if it's now taller, we've added a new level and we have to worry about these balance factors. Okay. And we're going to figure out what the root, again, this is recursive current root, what its balance factor is. And then either if it's -1, a 0, or a 1, we're going to have to do the balance from the left. Or we're going to change some things around. Okay. And then there's the other half of that where we insert into the right. Okay. And I think the traversal should be pretty much like we've seen before. So not much difference there. Okay. So this function will, or this header file implements an AVL tree that you should be able to look at. Okay. So that's an introduction to the idea of self-balancing trees, in particular about AVL trees, which I think are most commonly used. So the takeaway there on the AVL tree is you should be able to use the code. You should be able to create it if you had time, but we're not going to have time. So using the code will be a thing. And you should also be able to, on paper, determine what an AVL tree should look like. Okay. I will tell you, in looking for examples to give you, I used ChatGPT, which got the AVL tree wrong every time. So this is one of those things that apparently ChatGPT cannot yet do. So yeah, if you use ChatGPT for this, even to check your answers, note that the answers will not be correct. Not sure why. And then of the others, I think the B tree are certainly the most important, and understanding how those work is a good thing. If we have more time, we would do more with that. Um, but then in some cases, the 2-3 tree or the red-green tree could be useful. Okay. So if you have any questions about any of this, make sure you let me know. These are well, this whole class has been kind of complicated. This is not particularly much more complicated than it was before, but I guess it maintains that complexity.